Okay, so picking up where we left off from the last video, I'm going to take this equation here, and I'm going to do something similar to what I did over here. I'm going to take the derivative with respect to time. So I have the derivative with respect to time of dB dx, but I can change the order in which I take the derivative. So that is dB dt. And then I take the derivative on this side. Mu naught and epsilon naught are constants. So when I take the derivative with respect to time, they don't matter at all. So they can come outside. Okay, so now I have the second derivative of the electric field with respect to time. Now, this dB dt is equal to dE dx, so I'm going to take this and put it in for dB dt. So now I have the second derivative of the electric field with respect to x is equal to mu naught times epsilon naught times the second derivative of the electric field with respect to time, but I want to put the mu naught and the epsilon naught over on the other side. There we go. And so now I have an equation which just has the electric field in it and another equation which just has the magnetic field in it. And notice that the only difference between these two equations is that where you have a B in this equation, you have an E in that equation. Now it's time for me to introduce you to the general wave equation. So this is an equation in physics which you wouldn't have seen yet in a university physics class. You possibly may have seen it in high school, but the general wave equation says you take the second derivative of your function with respect to time. It's a partial derivative, and as I briefly mentioned before, these are really supposed to be partial derivatives, but we're not really concerned about that in this course. That is equal to b squared times the second derivative of your function with respect to x. Okay, so f is your wave. It's changing in time and also position, and v, very important, is the speed of the wave. So in this equation here, the magnetic field would be our function, f, and the speed squared is 1 over mu naught epsilon naught. Same thing here, but the electric field would be the function, but the speed would be the same. So we have two different wave equations here, and the speed for both of them, the speed squared is 1 over mu naught epsilon naught. So the speed is the square root of 1 over mu naught epsilon naught. Okay, now I want to figure out what that is, and we haven't really used epsilon naught that much, but we have related it to the constant k. So the constant k, which is equal to 9 times 10 to the 9th, I think I'll leave the units out and just trust that they work out. So that's our constant k, which is equal to 1 over 4 pi epsilon naught. So I could say then epsilon naught is equal to, multiply both sides by epsilon naught and divide both sides by 9 times 10 to the 9th, and you get 1 over 4 pi times 9 times 10 to the 9th with some units. Okay, and then I'm going to put that in for epsilon naught, and mu naught, remember, is 4 pi times 10 to the negative 7. So this is, epsilon naught is 1 over this, so since epsilon naught is in the denominator, the 4 pi times 9 times 10 to the 9th would go in the numerator, and mu naught is 4 pi times 10 to the negative 7th. So the 4 pi's cancel out, And if I have 10 to the negative 7th in the denominator, that would be 10 to the 7th in the numerator. 10 to the 9th times 10 to the 7th would be 10 to the 16th. So this is the square root of 9 times 10 to the 16th. Oh, actually, I would have liked it better. You can do it like this, but more exactly, K is 8.99. I think it's 8.995. Let me just check. We're just going to use 3 significant figures, so it's 8.99 times 10 to the 9th. Okay, so I could do 9 times 10 to the 16th, or 8.99 times 10. If I put that in for K, then it would be this times 10 to the 16th. Okay, and now we are going to take the square root. If I do it with just 9 times 10 to the 16th, that gives me 3 times 10 to the 8th. But if I do it with the 8.99, we're going to take the square root of that, and we get 2.998. Times 10 to the 8th. And can you tell me, and the units, since it's a speed, would be meters per second, can you tell me what this is? This was the speed of our wave, and this is the speed of light. So we have a magnetic field and an electric field, which are oscillating, and the speed of the wave is the speed of light. So this is our light wave, and this is the electromagnetic waves section. So our electromagnetic wave, which is made up of an electric field oscillating and a magnetic field oscillating, is a light wave traveling at speed c, which is the speed of light. So this brings us to this equation here. So the speed of light, I don't know if they gave it to me here. It's on the next page. Okay, so this is page 5 in the textbook. The speed of light, which is 3 times 10 to the 8th meters per second, which is what we get if we say K is 9 times 10 to the 9th. Or more exactly, if you say K is 8.99 times 10 to the 9th, you get 2.998 times 10 to the 8th meters per second, which still isn't the exact value for the speed of light, but it's closer. So these constants that we've been using in this course are actually related to the speed of light. And so we have our speed here, which is the square root of 1 over epsilon naught times mu naught, is equal to the speed. Here's our light wave moving at the speed of light. And see how we have, so this picture actually related to the picture that I drew here. Okay, so this is the y-axis, this is the x-axis. You kind of have to understand what you're looking at here. It might be easier if you look in the spiral physics version on the computer, on the M drive, because it's in color there and it might be easier to see what's going on. But the electric field is either pointing in the positive y direction or in the negative y direction. And so this wave, this red wave, is in the y-x plane. And the blue wave here is in the z-x plane. And so it's either pointing in, the magnetic field either pointing in the z direction or in the negative z direction. Okay, that's related to what I drew over here. I just assumed, and I had to make an assumption, we said, because we don't know enough math now at this point to be able to solve it without making these assumptions. So the electric field's pointing in the y direction and it's increasing. So here's my electric field pointing in the y direction and increasing. So we would be, for instance, right here. So the electric field's increasing. Well, if the electric field is increasing, by Faraday's law, that means we must have a magnetic flux pointed in the z direction. And our equation says the magnetic flux is changing with respect to time, and it would be increasing as time goes on. So your wave is changing in position, but also changing in time. So if you just stand still at this point, the wave, see the speed's going this way, the wave's going to come at you like this. So if you're standing at this point here, then because the wave's moving this way, the magnetic field at this point is going to increase. You could also freeze the wave in time and look at how the fields would change as you move along the x-axis. So they change with position and also with time. So you can stand at a single point and watch what happens at that point as the wave comes towards you, or you can take a snapshot of your wave, and so you're like freezing it in time, and look at what happens as you move on the x-axis. Okay, so we're going to stand right here. As the wave moves this way, first the magnetic field is increasing, like we drew here. Okay, but then if you wait long enough, eventually, like we'd be here on the wave, and it would start decreasing. Or maybe I could draw it like this. So it's going to decrease like that. Okay, and remember that we started off in a vacuum, so there were no charges and no currents. So you might wonder, if there were no charges and no currents, how did we have an electric field or a magnetic field to begin with? Well, this is the beautiful thing. If we go back to the equations that we have here, so Faraday's law says changing magnetic fields create electric fields. And Ampere's law says, well, now that we have fixed Ampere's law, so it says not only do currents create magnetic fields, but now we have changing magnetic fields, because that's a changing electric flux, which creates a magnetic field. So you have a changing magnetic field creating an electric field, but that electric field is changing and creating a magnetic field. So we have this self-sustaining wave of changing magnetic fields and changing electric fields, and that's what we get from Maxwell's equations. So there's a little bit more to this story. If we go back to my general wave equation here, f is a function of x and t, because you're taking derivative with respect to t and with respect to x, so it should be a function of x and t. And a is the amplitude of the wave, and then we have the cosine of 2 pi x over the wavelength. So for our general wave here, if you go from peak to peak, that distance would be the wavelength, plus 2 pi f t, where f is the frequency. It has units of hertz, which is 1 per second. And if you stand at a certain point, so let's say you stand here, and you count how many peaks pass you in a second, that would be the frequency. And so if you take this equation and take the second derivative with respect to time, and also take the second derivative, and remember they're partial derivatives, take the second derivative with respect to position, it should have this relationship. So let's just check and make sure that that is true. So I want the second derivative of this wave, the second derivative with respect to time. So if I take one derivative, that would be negative a sine of 2 pi x over the wavelength plus 2 pi ft. Then using the chain rule, I'm taking the derivative with respect to time, so I have to take the derivative of what's in parentheses with respect to time, so I get another 2 pi f. Then, whoops, that was just one derivative. Let's just do it like that. And then take another derivative with respect to time. The derivative of sine is cosine, so that's minus a cosine of the same thing, 2 pi x over lambda, plus 2 pi ft, but you have to use the chain rule again, so you get another 2 pi f. Okay, so that's the second derivative with respect to time. Now we need to take the second derivative with respect to x. Let's just do this all at once because it works pretty much the same except when you take the derivative of what's in parentheses. So you're going to have a minus a times cosine of 2 pi x over the wavelength plus 2 pi ft. But when you take the derivative with respect to position of what's in parentheses, you get 2 pi over lambda. So now you have a 2 pi over lambda squared. Okay, so now I'm going to put that into my equation here. So I have minus a times sine of 2 pi x over the wavelength plus 2 pi ft. All of, whoops, no, that was the wrong one. It was supposed to be a cosine times 2 pi f squared. So all of this here was just my original function. And then this is equal to b squared. And then the second derivative with respect to position is minus, let's just stick that up there, a times cosine of 2 pi x over the wavelength plus 2 pi ft times 2 pi over lambda squared. And this is just f also. Okay, so I can cancel out this. And this can make this positive if I make this positive. And then I have 2 pi f squared is equal to v squared times 2 pi over lambda squared. And then let me take the square root of everything. So I get 2 pi f is equal to v times 2 pi over lambda. The 2 pi's cancel out, and I can say the velocity, or the speed of the wave, is equal to the frequency times the wavelength. The frequency, remember, has units of hertz, which is 1 per second. The wavelength, that would be a distance here that has units of meters. So the frequency times the wavelength would have units of meters per second. And for a light wave, the speed never changes, so the frequency times the wavelength always has to be equal to the speed of light. So this is in the book also. Somewhere in the book. We have this equation for the electric field and also for the magnetic field. So this would be for a single wave, but in our light wave, we have the wave for the electric field and for the magnetic field. The electric field is changing in the y direction, so this is pointing in the j hat direction. The magnetic field is changing in the z direction, so the magnetic field is pointing in the k hat direction. Other than it being a vector equation, it looks just like what we have here. A is the amplitude, so that would be the maximum value for the electric field or the maximum value for the magnetic field. I thought that this was somewhere in the book, but I don't see it. If you go on the M drive to the electromagnetic waves folder in my course folder, there's a file called Visible Spectrum, and it shows you for different wavelengths what kind of light waves you would have, and remember that as the wavelength changes, the frequency would have to change also, because the wavelength times the frequency has to equal the speed of light. So as the wavelength increases, the frequency would have to decrease. And the wavelength or the frequency would determine what type of electromagnetic wave it is. So you could have gamma rays, X-rays, visible light waves, microwaves, and radio waves. So you can either look at that from the file on the M drive, or you can just Google the visible spectrum. So that is almost the conclusion of what we have here. There's just a few other things from the book to take a look at. So in our light wave here, the magnetic field and the electric field always have their peak value at the same time, so the waves are in phase. When one field is at 0, the other one is at 0 also, and they're both at the maximum value at the same time. The angle between the magnetic field and the electric field is always 90 degrees, and the direction that the wave goes in is given by the cross product of the electric field and the magnetic field. So if you put your fingers in the direction of the electric field and then point them in the direction of the magnetic field, this is the direction that the wave is going in. And finally, one other thing, the ratio of the electric field to the magnetic field at any point in time is equal to C. So if you look at any point along the wave here and take the ratio, you get the speed of light. Okay, so we're gonna stop here for now.